Welcome back. In the previous video, I talked a little bit about the process of generating a Segwit transaction, and I sent few coins to myself, and in these tutorials I'm going to spend those coins. Now, I want to start this tutorial by showing you some of the resources that I am using, because as I mentioned in the previous video, the Bitcoin documentation is kind of all over the place, and I believe it will be beneficial to know where you can find most of the relevant information. The first item is this BIP 143 documentation, and especially this list over here. This documentation talks about how to sign and how to serialize a Segwit transaction. And it also contains some basic information and a few examples on how to create this type of transactions. Basically, our goal in this video is to follow this documentation in order to create the witnesses field. Another resource is the flowchart. I've incorporated this BIP 143 list into my flowchart, and this flowchart basically sums up all of the steps that are required in order to create the witness field and the final transaction. And you are going to go back to this flowchart quite extensively during this tutorial. Another very important resource is Bitcoin's developer reference. In here we can find information on how to properly serialize each individual field in our transaction. So we are going to go back to this documentation quite often. The last resource is blockchain.info. This is a simple yet very efficient blockchain explorer that I will use whenever we need to extract information from the blockchain itself. More specifically, information about previous transactions. So those are the resources that I'm going to use. Keep that in mind. I will leave links to all of those resources in the description below. And now that we finally got this out of the way, we are finally ready to start working on our witnesses field. The first item on our list is the version field. This field is described in the Bitcoin's developer reference, and basically it is a general field that tells the other users what type of messaging convention I am using. I am using the default one, so I will set my version field to be 1. And as you can see, it should be serialized as a little endian unsigned integer 32. Back to our code. This is the version section. So let's make a comment here, version. And the version field should be equal to 1, 2 bytes, 4 byte long, byte order is little, and it should be unsigned integer. So signed equal false. Items 2 and 4, they are both related. The hash previous output, which is item number 2, this is basically the result of the double SHA-256 over the outpoint, which is item number 4. Now, what is the outpoint? The outpoint is the origin of the coins that I am about to spend. In the Bitcoin developer reference, we can find more information on how to serialize this outpoint field. And we can see that the outpoint itself is made out of 2 fields, the transaction ID and the index number. Both of those fields can be found on the blockchain. The first one, which is the transaction ID, this field should be serialized in a little endian, which basically means that we are going to reverse the byte order that we will find on the blockchain explorer. And we will see how to do that in the code in a minute. And the second part is the index number, and this one should be serialized as a little endian unsigned integer 32. So once I will get my outpoint, I will then take it and I will use my double SHA-256 function to get the hash previous output or the hash previous outs, which is the second item on our list. So by following this step, we will basically going to get two items, items number 2 and item number 4. Okay, in this section, we are going to create the hash previous output and the outpoint itself. And in order to create those two items, we need to begin by creating our outpoint. And the outpoint is made out of the transaction ID, which in this case, we are going to take from the blockchain. It's byte from hexadecimal. And this is the transaction ID that I took from the blockchain itself. And of course, I need to reverse the order of the bytes. So I'm going to reverse it using the Python reverse function, like so, -1. And the index number is 1. And so 1. And we are going to convert it to bytes, 4 byte long. The byte order should be equal to little, and it should be unsigned integer. So signed equals to false. Now let's make the outpoint. And the outpoint is basically the transaction ID plus the index. So outpoint equals to transaction ID, there we go, plus the index. And now we can say that the hash previous output, equals to the double SHA 256 of the outpoint. And there we have it. The sequence field, which is item number 7, is a bit of a weird one, because it is meant to be used in a more complex type of transaction. However, we are creating a basic Segwit transaction, so we will use the default value of FF, 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 FF. And as long as you don't try to create a transaction that can be replaced, and in this video we are not going to create such a transaction, this value will always work. Once we get our sequence field, we can use our double hash function in order to get the hash of the sequence, just as we did in the previous part with the hash of the outpoint. Okay, so let's make the code for the hash sequence plus the end sequence. So let's make a comment here. We are working on the sequence plus the hash sequence. Hash sequence and the sequence itself. And the sequence equals to 4 times FF, and we can convert it directly from hexadecimal, so bytes from hex, and FF, 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 and again. And the hash sequence, this is simply the double SHA 256 of the sequence field. We got 2 more items. We are skipping item number 5 for now. We will get back to it soon enough. And now we are dealing with item number 6. This field is for the input amount, how much Bitcoin I received. In this case, the amount equals to 0.00135501 Bitcoin. And this information should be serialized as little endians, signed integer, 64 bits long. Now a quick side note, the difference between the input amount and the output amount goes to the miner as a miner fee. And that is something that is worth remembering when we are creating the output of the transaction. We will see it soon enough. Okay, so this is the value/amount field, and I'm just going to call it amount because there is another field that is called value later on. So just to make it more simple, this will be equal to amount. And the amount should be equal to the input amount. And we need to convert it into an integer. Pay attention, this is quite important because the default type in Python is a float. So the input amount should be 0.00 135501 Bitcoin, but the developer reference says that this number should be represented in Satoshis. So I'm going to multiply this number by 100 million, and I'm going to convert it to bytes. The byte order is little endian, and this integer is going to be signed. So signed equal to true. A bit weird, but this is just the way it is. There we have it, the amount field. In these steps, I'm going to create two items. The hash output, which is item number 8, and the output itself. However, only the hash output is used to create the witnesses field. And the hash output is, and I hope that you already guessed, the result of the double SHA-256 over the output itself. Now, the output is a field that we need to fill by ourselves. And we can see in the Bitcoin developer reference that this field contains 3 pieces of information: the value, the size of the public key script, and the public key script itself. The value is quite simply the amount of coins that we wish to send. And you can see that this information needs to be serialized in little endian, signed integer, 64 bits long. The second and the third fields, the public key script and the public key script size, they basically correspond to the recipient address. And the script is a piece of code that other Bitcoin nodes need in order to verify the correctness of the transaction. The script that we specify in the output of the transaction is the script that the recipient needs to be able to solve or to prove in order to claim their coin. The most common script says something similar to this value will go to anyone who can prove ownership over the following hashed public key. Now the recipient will prove their ownership over this hashed public key by signing a transaction with their corresponding private key. In my example, I created a script that will send this value to a pay-to-script hash over pay-to-witness public key hash version 0 address that I control using my private key. And again, if you don't really remember or you don't understand the relation between the script, the key, and the address, please watch my tutorial on keys and addresses. Okay, so now we are going to create the hash output and the output itself. So let's make a comment, hash output, and the output itself. And we know that the output is made out of 3 fields. The first one is the value, and the value is the amount of bitcoins that I want to send. It should be again converted into an integer, and it should be presented in Satoshis. And in this case, I'm going to send 0.0013 Bitcoin. The difference between the input amount and the output value will go to the miner as a miner fee. And just as in the case of the input amount, it should be 8 byte long, the byte order is little, and it should be a signed integer. Now the public key script, I'm going to basically copy it from the input of the previous transaction, from the output of the previous transaction. And this is of course something that you should avoid, because by copying this script, I am basically reusing my old address. This is something that is really not recommended, but if it is only for educational purposes, or in the case of this tutorial, I believe it should be good enough, and hopefully it might even be slightly easier for you to follow the steps of this tutorial. So just for the educational purposes, it will be okay to reuse this address. Again, in real transaction, please create a completely different and new script that will correspond to a new Bitcoin address. So now that I got my public key script in place, I can basically check its length and store it as another variable, as another field. So the public key script length should be equal to the length of the public key script. And I'm going to serialize it as 1 byte long, little endian, even though it is only 1 byte, and it should be assigned, and it should be an unsigned integer. So signed equal false. Now let's combine those three fields into the output field. So the output is going to be equal to the value plus the public key script length, so length, and the public key script itself. And now we can create the hash output as the result of my double SHA-256 function over this output over here. Then there we have it, the hash output and the output itself. The nLocktime field is another field that we are not going to spend much time on. The nLocktime is usually used in more complicated type of transactions, usually in conjunction with the Lightning Network. For basic transactions, the default value should be 0. And the Bitcoin developer reference says that it should be serialized in little endian byte order, unsigned integer 32. So let's make the nLocktime field. This is very simple. Let's make a comment here for nLocktime, nLocktime, and this field, nLocktime, should be equal to 0, and it should be converted to bytes, 4 byte long, little endian, and unsigned, sign equal false. There we have it, simple field. SigHash, or item number 10. What type of information we are going to sign? Again, we are going to use the default value for basic transaction, which means to sign all. For some reason, this value cannot be found in the developer reference, so you'll just have to trust me when I tell you that the value should be equal to 1 in little endian byte order, unsigned integer 32. The SigHash field is another very simple field, so I'm just going to make a comment for it, SigHash, and I'm going to take its value from the table that I showed you earlier, and I'm just going to reverse the byte order. So it's going to be bytes from X, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0. That's it. Now we got another field that we should be able to generate by ourselves, and that is the private key and all that follows it. Using the private key, we will generate 4 main items. We will generate the script code, the compressed public key, the hashed public key, and after we have completed our BIP 143 serialization, we can also create the signature. The compressed public key and the signature will later be used to create the witness field. The hashed public key will be used to create the script code. And we can see in the BIP 143 documentation that the script code for the type of transaction that we wish to generate is 1976 A9 14, the public key hash 88 AC. And some of you might have already noticed that this is also the pay to public key hash type of script, the all type of transaction script. And that is actually a very good example of the way that the Bitcoin protocol sometimes maintain outdated data in order to be somewhat more backward compatible. Okay, so back to our code. And in this section, we are going to work with ECDSA and with the script code. So script code. And the first thing that I'm going to do is to import the ECDSA library. and to insert my private key in its hexadecimal form. Now be very careful when you are working with your private key. Make sure it is not really associated with a wallet in which you are storing a substantial amount of Bitcoins. I would recommend create a special address for this private key that will contain no more than $5 or $10 worth of Bitcoin, so that even if you do make a mistake, it won't cost you so much. The process of going from the private key to the compressed public key and the hashed public key is something that I've already talked about and demonstrated in my previous tutorial on keys and addresses. And this is why I'm just going to copy paste the code from that tutorial. If you are not so sure how to get this code, please rewatch my previous tutorial. I will leave a link in the description below. But basically we just created our compressed public key and our key hash, and we can use our key hash in order to generate our script code. And the script code is defined in BIP143 as the following script. So I'm going to create another byte object from hexadecimal with the following script: 19, A9, 14, followed by the key hash in its hexadecimal form. Don't forget to convert to hexadecimal. And then 88 and AC. So 88, AC. And there we have it. This is the script code. And now that we got our script code, we can finally create our serialized BIP143 object. And this is basically a list of all the items that they created. We got the version. The next item should be, if I'm not mistaken, the hash previous output. Just a second. Yes, it is the hash previous output. Then we got the hash sequence, followed by the outpoint, the previous input, followed by the script code, and then the amount, if I'm not mistaken. Yes, the amount, followed by the sequence, then the hash output, and then you also realize that I made a mistake at the beginning. It should be hash previous output. I made a typo there, so let's fix it. So this is the hash output. Now we got our Locktime, and finally the SigHash. And that's it. This is the serialized BIP143 object. I'm now going to hash it using my double SHA-256 function to get the hashed BIP143. So the SHA-256 of the BIP143. And this will be the object that I will sign, this hashed BIP143. I will create a signature using my sign-in key. The method should be sign digest. I'm going to sign the hashed BIP143. And I'm going to specify a type of encoding which will make it easier for me to work with this signature. And this encoding will be the ECDSA util sign encode DER canonized. This is quite important. Keep this format. It will help you a lot later on in the tutorial. Okay, so I got my signature, I got my public key, and now it is time to create the witness object. The first thing I will do in my witness object is to specify the amount of items in that witness field. And there are two items, the signature and the public key. I'm going to start with the signature, and I'm going to insert the length of the signature, just as we did earlier for the public key script. The same process. So the length of the signature converted to bytes, little endian byte order, and it should be unsigned. Now the signature, the next byte, this one is called the separator. It will separate the signature from the public key, and it is defined as 01. And I'm going to insert the public key, but first, just as I did with the signature, I'm going to start with inserting the length of the public key. So the length of the public key, 2 bytes, 1 byte, little endian byte order, signed, and then the public key itself. And there we have it. And in the next video, I will use this witness field and some of the other fields that we've worked on in this video to generate the final transaction. So thank you all for watching, and I see you soon.